Okay, so let me carry on. So, where are we now? So basically what we have shown so far is that at low energies or large distances, the physics of the XXZ chain is described by a free boson. And what I used also so far still is that delta was small. Yeah? And that does not mean I'm doing perturbation theory in delta. You can try, so because there's another homework session in the afternoon, so that would be your homework, trying to solve the model by doing perturbation theory in delta. You will find that you fail. Alright, so it's not perturbation theory what we're doing, in the sense it's a particular resummed version thereof. But so far I still have used that delta is small. Okay, and how to do large delta, we'll see in 45 minutes maybe. So, this is quite a surprising result if you think about it, because this XXZ chain was exactly precisely equivalent to a theory of interacting fermions. Okay, so these fermionic modes, they interact in a manifest way. But what this mapping basically tells us is that at low energies, large distances, there's a different basis, yeah, which is the basis of bosons, curiously enough, in which the theory becomes free. Okay, and that wasn't obvious to begin with. So now, the piece of information that is still missing, we really want to be able to calculate correlation functions for the lattice spin model. So what still remains to be done is we have to work out how spin operators, lattice spin operators, translate into this free boson theory. Yeah.
The thing that we have to take a small parameter of delta means that this is not exactly an integrable model. I mean, you said that it was not exactly like doing perturbation theory, but it's not exactly like you have all the model. I mean, you have to make some expansion, so you have to.
Well, okay. So how did I use that delta was small? Yeah. So I basically used that delta was small to have a good starting point, because my starting point was just the XX model. Yeah. And then I defined everything relative to that starting point. Yeah. If I wanted to start with delta equals a half or so, I wouldn't know where to start. Okay? So that's why I assume delta is small. So I'm in the vicinity of this XX model. But the consideration that we have done there is actually valid throughout this phase. Yeah? So the only thing I have to do, but this we will see in a little bit, I have to choose the correct value for this R tilde and for the velocity of the free boson Hamiltonian. So these parameters I have to adjust. Yeah? But these formulas actually are valid throughout the entire phase. Okay? Moreover, does it have anything to do with integrability that I end up with this free theory? The answer is no. There's nothing to do at all whatever with integrability. I could do the same calculation for a non-integrable model. Add some junk which makes the model non-integrable. This approach will go through. No problem. Yeah? The only issue you always have when you do this postgraduate approach, you end up with these parameters of the free boson theory, namely the velocity and the radius. And then, if you wish, also kf. Right? And you need some way to fix them. The way I have fixed them was by starting at the XX model and then taking delta to be small. Fix them. In general, I don't know how to fix them, and you don't know how to fix them either. Yeah? For a general non-integrable model. So, what you have to do then is either you have an integral model like you do for the XXZ chain here, then you can use information from integrability, and I'll tell you how, to fix them. Then you get exact answers. Alright? Or if you don't have that, typical situation. Then what you have to do is you basically have to say, well, this radius is, for example, related to the scaling of energy levels of excitations in the finite volume. Okay, which is something you can calculate numerically by using density matrix normalization group, something like this. So by doing a numerical calculation, which with this algorithm is fairly standard nowadays, you can fix what R tilde is, you can fix what V tilde is, and then you're in business. You know? So that's basically how the story goes. Integrability was irrelevant for what I've done so far. Okay? So this bosonization scheme is much more general. Yeah? It doesn't hinge on integrability, but integrability is very, very useful for fixing these parameters when delta is no longer small. Okay? Were there other questions? No? Okay, so then let's see how to bosonize spin operators. So we want to know how to translate Sz and Sx in terms of into the free boson so that we can calculate spin correlation functions. Okay, let's start with Sz because that is easy. So Sz was actually local in terms of the fermions. So I can write it like so. Okay? And now the only non-trivial piece is this normal ordered operator, because this is just a constant, which is equal to the magnetization per site. And this one just becomes a naught right dagger right plus left dagger left, normal ordered. I mean, so basically use what these operator products mean is the same as last lecture. Yeah, point split and then the divergent piece subtracted. Plus e to the minus 2 kf ix, and then we have a right dagger left, and finally e to the 2 pi kf x left dagger right. Okay, and now last lecture I had here on the blackboard all the bosonized expressions for these bilinears. All four of them. So now let's just yeah, so they're written here. You still have them in your notes, I hope. So I plug them back in now, and then I simply express the old Bose field, if you wish, in terms of this new one. So I express everything in terms of this phi tilde and theta tilde. And what I get is something like the following. So, that's what I get. Okay, so this piece simply comes from the right dagger right and left dagger left. Yeah, so that was before just dx phi divided by square root of pi. And once you do the correct rescaling between phi and phi tilde, you pick up this extra factor. Okay, and these two pieces, after you bosonize them, it gives rise to this operator here. Okay, so that's the bosonization of the Z component of the spin. And you see, at low energies, it has essentially three. So the Fourier components live in momentum space around 0, which is this part, and around plus minus 2kF, which is this part. Okay.
What is B?
So B, if you actually do this calculation, so B comes out to be 1 in this calculation. So what it means, when delta is very small, then this amplitude is goes to 1. All right, but in general, and I hope I can get to this at some point, you have to take into account corrections to this Bose-onization formula which emerge for larger values of delta, and what they do is they change this coefficient from 1 to a function of delta, which is non-universal. And then there also are further contributions which you pick up here. And these further contributions, they will, roughly speaking, look like this one. But instead of 2kF, you will get 4kF, 6kF, 8kF, and so on and so forth. So these are called higher harmonics, and their coefficients are such that in the limit delta goes to 0, the coefficients actually go to 0. So at delta equal to 0, they're not there. Okay, you acquire them as soon as you go away, but their coefficients usually small. Yeah. And moreover, in the correlation function, these contributions, they decay very, very quickly. Okay, which means the leading behavior at large distances is just given by the first few terms, which are the ones here. And this is the formula you usually find in the literature. And well, people don't usually talk much about these terms because they're much less important. But there's a simple way to understand where they come from, and hopefully we'll do that tomorrow. Okay, now let me actually use this straight away to work out what are the spin correlation functions. So that you see this is a quite powerful technique. Alright, so now what I want to work out is ground state correlation functions as z j plus L as zj. So I start with an equal time correlator. Okay, now I substitute this expression. And so I get, okay, so I get something which is like m squared, as a constant. And now I get the contribution in this one. So I have a naught squared divided by 4 pi squared r tilde squared dx phi tilde of x dx phi tilde of 0. Okay, and then we have plus b squared over pi squared sine phi tilde of x divided by r tilde minus 2k of x sine phi tilde of 0 divided by r tilde. Okay, where x now is L times the lattice spacing. Okay. Now, what about the cross terms? So the cross terms, because I haven't written them, they cancel. Is it obvious to you why they will cancel? Well, okay, so essentially you can just think about obtaining this dx phi tilde as a limit of one of these vertex operators, where you take, so you basically start with something like this, e to the I alpha phi tilde, take the derivative of this, roughly speaking, 1 divided by alpha, and consider the limit alpha goes to 0, something like this. So this would be a way to make dx phi from a vertex operator. But then, if you have a correlator between dx phi and e to the I alpha phi, you can immediately see this must be 0, because the only correlation functions of vertex operators that were non-zero where you have e to the minus I beta phi e to the beta phi, which is not the case here. So this clearly cancelled, and so this is what we're left with. Okay. Now, how do we work this out? Well, this one is straightforward, just from the mode expansion. It's the same type of calculation we did last week. All right, and this one, we can just use the formula that was on the blackboard last lecture, where we have the product of vertex operators. Normal ordered vertex operators. So you just write the sign as e to the I phi plus minus e to the minus I phi, and you work it out. Okay, so now, in terms of this free boson theory, to work out these correlators is really straightforward, and it gives us an answer. And the answer is like so. So I start with this constant, and then I have plus 1 over 8 pi q r tilde squared. Here I get an a naught divided by x, where am I here, squared. And this one becomes plus b squared divided by 2 pi squared cosine 2kf x. And here we have a naught divided by x divided by 1, 2 pi r tilde squared. Yeah? And that is the answer. So now, what you have what is actually an exact result for the large x behavior of this spin-spin correlation function in this Heisenberg XXZ chain. It's exact once you know what R tilde is and what B is. Okay? But in particular R tilde, I'll just tell you how it's done. That tells you, for example, what is the exponent here of this power law decay. Yeah? And that would be exact. Right, so it's quite a far-reaching result. And importantly, so now you see there's this smooth component here, which always goes like 1 over x squared, independently of delta. And then you have this 2kf component, which is also like a power law, but the power law actually depends on delta, because it's R tilde dependent on delta. What the interactions do is they shift the power laws. Alright? So that's already very nice. But now in principle, of course, you can go further. So this was an equal time correlation function. And I just should say you can check this now. I mean, you can compute this numerically with the MRG or something like this and compare it to this kind of formula, and you see it works very well. But now, of course, you can go further. So you can say as well, why should I stick to equal time correlators? So let me just look at a non-equal time correlation function. So what about this one? Okay. Now I can just use my dictionary, translate it into a correlation function that we actually use this formula. That's one of the advantages of working on the blackboard. So now we make this time dependent. Where does the time dependence go? So it goes here, and it goes here. Yeah? But you see, this is unaffected, etc., etc. Okay, and now we once again have a correlation function in a free bosonic theory. So we can just work out what these time-dependent correlation functions now are. Okay, so for these chiral bosons, remember, the right-moving field that we introduced originally just depended on x minus vt and the left-moving one on x plus vt. So for these chiral vertex operators, you can immediately restore what the time dependence is. Okay, and that goes through, basically tells you what time dependence you have here. Okay, so we can restore the time dependence, and what we get is the following answer. So m squared just stays. Yeah, and then we have plus 1 over 8 pi cube power to the square. And here I can find something which looks like this. X squared plus v tilde f squared t squared divided by x squared minus v squared t squared. And then we have this b term, v squared 2 pi squared cosine 2kfx a naught squared x squared minus v squared t squared 1 divided by 4 pi. Okay, so now we even have the non-equal time correlation function, the dynamical correlation function. Okay, which is very nice. And now what people already did, I don't know, a very long time ago, 20, 30 years or so, they were very interested in these dynamical spin correlation functions in the Heisenberg model for this reason I told you about in the first lecture, which seems a very, very long time ago now, I can imagine. So I told you that there is this quantity called the dynamic structure factor, which is something that's measured by neutron scattering, which is related to the Fourier transform of this object. Okay? But in those days, in the 80s, there was no way of calculating this in any way. And then the first way, you know, people succeeded in doing so, so they used precisely this formula, essentially. Now Fourier transformed it, yeah? And that gave them then an approximation, yeah, because this is only a low energy approximation, to the structure factor in the Heisenberg XXE shape. Yeah? It's given in terms of some gamma functions. I'm not going to write it for you. You can look it up in the literature. And it was done by Heinz Schulz in the 80s. Okay, so now just to check whether anybody is following, this structure looks a little bit funny. I mean, so why could you have guessed this? Is there any principle that might tell you what this function should look like, what kind of structure this function should have? Well, Andrea knows, but I'm not going to ask him. Surely there's somebody else. Famous last words, yeah.
First of all, is it correct? Because
it's always a good question. Yeah. I think it is, yeah. No.
You said D was zero, then you're not. There was zero.
Okay. Yeah. Thank you. Now let me repeat my question. boson theory, I give you a hint, is relativistically invariant by construction. No? Still nobody. All right. This operator, is it Lorentz invariant? Perhaps not. No, so it basically it transforms like a component of a vector. Yeah? And so now using the Lorentz invariance of the theory, yeah, you know that the correlation function basically has to have the right transformation property under Lorentz transformation. And that basically tells you it should look somehow like this. Alright? Whereas this operator is a scalar, yeah? So therefore the corresponding contribution to the correlator should be invariant, which it is. Yeah? X squared minus t squared, c squared t squared. So this is quite a useful consistency in these calculations. If you do this calculation and you get out something which has the wrong transformation properties, you made a mistake. More likely than not. But of course, this one, well, alright. Now, that was the longitudinal correlator, so that was the easy one. So now, and it's quite nice. I mean, so you shouldn't underestimate how nice a result this was when they took the Fourier transform and got something that was comparable to what they saw in Newton's calculus. And to take the Fourier transform is essentially an exercise in contour integration, which I leave to you for the afternoon problem session. Or you can ask Pasquale, because he likes to do contour integration. So, now what about the Sx and Sy? So they're much more difficult. So, now let me do S minus, which using the Joule-Dicker transformation I can write in this form. So this minus 1 to the j minus 1 comes from the fact that in the Joule-Dicker transformation I had a minus 1 here. Yeah. But that just gives me an overall factor which I wrote in this way now. So this was, and of course this is just Sx j minus I Sy j. So now I want to work out how to bosonize this. And immediately you see what the problem is. The problem is this chap here. So the string operator is not local. So you might think at first sight, well, maybe we're there, right? Because it's a local, let's give up. Well, let's not quite give up yet. So let's look at this string operator here. Curiously enough, it will turn out to be local after the dust settles in terms of the boson. So let's see how that goes. So I start by rewriting it in terms of normal order pieces plus C beta L C. So I have something like this. Yeah, so L less than J, so I have something like this. And then what I do is I explicitly symmetrize it. Okay, and I do this just to make manifest this operator actually might not look like it, but it's Hermitian. And the easiest way to see its Hermitian, in terms of the spins, it actually was the product L less than J, something like 2SZ minus 1 or something like this you had in there. And that clearly was a Hermitian operator. Yeah? So this operator is actually Hermitian, and so therefore what I'm doing is I just add itself and divide by 2. Okay? It's useful to make it explicitly symmetric. Yeah, and so now what I want to use essentially is that the C dagger LCL, that's the density of fermions, and so that goes like KF A naught over pi. Okay, so that would be these pieces. And this lower order density we now bosonize. So L less than J, C dagger LCL. Okay, now what I do is I use my favorite formula. First go to the continuum limit using that CL was square root of A naught right of x e to the I k f x plus left of x e to the minus I k f x. Yeah. And then I use my bosonization formulas. Okay? And the sum will turn into an integral. So this goes to something like integral to x dx prime. And here I have minus 1 over 2 pi tilde dx phi tilde of x prime. And here we get another piece plus eta bar over pi a naught squared sine phi tilde of x prime over r tilde minus 2 kf x prime. So something like this. Okay? Now what I will do is a little bit dodgy. So now come a bunch of dodgy, somewhat dodgy manipulations. So I will once again drop this contribution, yeah, simply because it has this rapidly oscillating factor. Okay? But it's a bit dodgy now because after all my integral just goes to x. Yeah? And it's so this term supposedly will give a contribution from the vicinity of the upper integration boundary, but I simply will ignore this. Yeah? So it's somehow supposed to be small. Okay? So we drop this, and then you see what remains is essentially an integral over, dx phi tilde, which I can integrate back up, and then I just get a phi tilde. Okay? So, and this suggests, that the string operator e to the I pi L less than J, C dagger LCL should become something like 1/2 e to the I kfx e to the minus I phi tilde of x divided by 2r tilde plus Hermitian conjugate. All right. Now we can use this to get bosonization formula for S minus. Oops. So in S minus, I have to multiply this by Cj, and Cj once again was just well, it was a square root of the naught also, it matters. E to the I kfx eta, well, this one actually cancels square root of 2 pi. E to the minus I tilde divided by 2r tilde minus 2 pi r tilde theta tilde plus the other piece. Tilde divided by 2r tilde minus 2 pi I r tilde theta tilde. So that's what we basically had shown before, and so this is perfectly kosher. This one is, this derivation is a little bit dodgy, obviously, but I mean, so it does extract the most important pieces. And now all that remains is you have to take the product of these two. Okay? And now this once again involves the products of these vertex operators, but this we know how to do. Okay? And so then multiplying these two to come up with the following expression. Sj minus goes like some amplitude times minus 1 to the j e to the minus 2 pi I r tilde theta tilde plus some other amplitude a minus 1 to the j times a big bracket e to the 2i x e to the minus pi tilde divided by r tilde minus 2 pi r tilde theta tilde plus the other piece. Well, okay, let me write it. Minus 2i x e to the I tilde over r tilde minus 2i r tilde. So that's the Bose-Normalization formula for S minus, where A and C are two amplitudes which in this kind of calculation are not controllable. So these we can't really say anything about. Now, as you saw, this calculation with the string operator, so that was by no means a rigorous calculation, but it was a little bit hand-wavy. It gives the right answer. It's a reasonable calculation, but you might question the validity of the outcome. Okay, and a more robust way, if you wish to derive this, would be as follows. Okay, so you have this lattice spin operator, and you have the XX Hamiltonian. And the XX Hamiltonian has a variety of symmetries. So it has a U1 symmetry, which is rotations around the z-axis. Then it has discrete symmetries like parity, reflection around the origin, and in zero magnetic field it also would be time reversal invariant. So there are a bunch of these discrete symmetries. And moreover, we know how this operator transforms into all these symmetries. Okay? And what you can do now, it's a little bit of work, but not too bad. You can just work out how these symmetries are implemented on the level of the free boson theory. Yeah? The free boson theory will reflect these symmetries, discrete symmetries, and the continuous one symmetry of the XXC Hamiltonian. And then what you do is you can say, let me simply write all the operators, yeah, that are compatible with these symmetries. Okay? And what you will find is, you get operators like the ones, like exactly the ones I have written, so they are allowed, plus many more. Okay. Now the question is, which are the important ones, which are the unimportant ones? Okay, and once again, the organizing principle is the scaling dimension of the operator. So, depending on what the coefficient here is, yeah, in the exponential, the correlation function of this operator, there always will be k as a power law, but it can be a very high power or low power. Okay. Now, for calculating correlation functions, we're interested in the lowest possible powers. And what the lowest possible powers are, that we already calculated, and Professor Mussardo will explain this a little bit more, how the power laws and the correlation functions are related to the energy levels in the finite size spectrum of the Hamiltonian. And to cut a long story short, the lowest possible scaling dimensions are exactly the operators with the lowest possible scaling dimensions are exactly the ones I have written here. Yeah? And then, if you go by the symmetry argument, there would be many others. Okay? It gives you the same answer. So this is, in spite of the somewhat heuristic variation, so this is a very, very precise formula, which we will use tomorrow just to work out what the correlation function is. And so I think we stop here today. And no questions allowed because we want to have lunch.